Good morning. Welcome to Krishna's class. Today we prove an important result which related to the locally compact Hausdorff spaces, which is essentially a tool that we require to construct a sequence of functions. We shall see the details of this later, but let us now look at the result. Now let me this is the theorem that we are going to write in here. So we prove the following theorem. Suppose X is a locally compact Hausdorff space and let U be open in X. That means X we are taking as a topological space. So we are working on a topological space X tau, which has the property that it is locally compact. It's a locally compact Hausdorff space. Then there exists so the statement is let K be a compact then there exists an open set V. There exists an open set V with compact closure such that K is contained in V, the open set V, which is of course contained in the closure, and that is contained. That means squeezed between K and U, you have an open set whose closure lies between V and the open set and the given open set. The Venn diagram representation would be, so you have a topological space X, which is assumed to be locally compact and housed up. So you have a certain open set. It need not be something bounded, but this just schematically I am representing 2 is. This is open. Now there is a K compact set which is contained in K. Then what we assert is that there exists a open set E such that its closure, such that V closure naturally V. This looks a sort of, for instance, we take R2, then or take R1. So, for example, you take R1, which is a locally compact Hausdorff space. Locally compact Hausdorff space means every point as a neighborhood whose closure is compact. That is what we mean by locally compact. Then Hausdorff space means given two distinct points in the space, you can separate them using open sets. So R1 is an example. For instance, Rn has this property. Now let us take a compact set. So let K be equal to, it's a closed bounded interval which is compact. Okay. Now let U be some subset of R1 which is open and K is contained. So this is the scenario. This is the closed set I am talking about. This is the closed set I am talking about. Or this is the compact set K I am talking about. Now this is contained in some open set. Okay. So U is open, not necessarily bounded, it can be unbounded. So it can be the whole space also, as we shall see while proving the theorem. Now you see that you can find an open set V CD contained in U. The scenario may be quite complicated if AB is not an interval, okay, but a compact set. Okay, then contained in CD, and this is obviously contained, its closure is, and that is contained in the given, whatever it is. So this is the scenario that you have when you, a very simple situation that you examine. Now this would be required because there is a open set that squeezes between the given open set and the compact set, such that its closure is again contained in U, then it's a very nice result. I mean, for instance, you cannot have, suppose U is equal to CD. Okay, so your V cannot be C, say E or something like that, because what happens is V closure is equal to then CE, but CE is not contained in okay, but then you can always find, suppose you have this U is an open set, you can always find some open set CD which is squeezed between U and the compact set, such that the closure of the open set is also squeezed between U and the compact set. Okay, so that's the result that we do. Essentially tells you, suppose you want to build a function which takes value 1 and takes value 0. Okay, so what you have is this. Suppose the function, the graph of the function is something like this. This takes the value 1 and takes the value 0 here. Then you can patch up these two in such a way that you have a continuous function. So that means there is a gap between C and A, there is a gap between B and D, so that you can patch it up continuously on this. Now this is the sort of application that we are after. So that's just a hint to what is to come, but we have to build it in a general scenario, and we have to prove this theorem. Okay, so let me just try to prove this result, but before that we need some tool to prove it. So we'll take another theorem, which is a supporting the above result. Or a tool that we need to prove this result. So let us first take that statement, theorem. Let if K alpha is a collection of compact subsets compact subsets be a collection of compact subsets of a There's a nice separation between points is assured in the space. And if intersection K alpha empty, then there exists some finite subcollection of K alpha having an empty intersection. So we are having the situation that K alpha is a collection of compact sets with the property that intersection K alpha is empty. Then there exists some finite subcollection, say K1, K2, etc., Kn of this collection K alpha having an empty intersection. Now this is the summary. Okay, let's prove this here. So we'll use the separability criteria that is available and compactness of the space in proving this result. To prove this theorem, we have to, in a way, construct this K1, K2, etc., Kn. How do we do this? So we start with an arbitrarily picked compact set among K and K. Now you see that define V alpha to be equal to K alpha comma. Then V alpha is open. X is a Hausdorff space. Okay. Now put fix some K1, some element, pick an arbitrary connection. Then no point K1 belongs to why? Because is empty. I mean, suppose K1, there is a point of K1 which belongs to every one of these K alpha. Then what happens? You cannot anymore say that intersection alpha K alpha is. That's a contradiction. Okay. So that the reason is this is empty. Therefore, you have K1 is, not every point of K1 belongs to every one of these K alpha. Okay. So now to take V alpha. V alpha is an open cover for K1. Therefore, since K1 is compact, there exists V alpha 1, V alpha 2, V alpha n, which is a subcover for K1. That means K1 is contained in okay. Therefore, now look at this one. K alpha 1, P alpha 1 complement. Sorry, P alpha 1 complement, intersection V alpha 2 complement, etc. Complement. What are they? This is equal to K alpha 1 intersection K alpha 2 alpha n by definition. Okay. Now you take the complement of K1. So you have therefore from this relation, that is K1 is contained in take the complementation. You take the complementation, this is what it is. V1 K alpha 1 intersection K alpha 2 alpha. By taking just the complement. What does this mean? This implies K intersection K1, which is the complement of this intersection PC is empty. Now this is the conclusion that we can draw. So that completes the proof here. Okay. Now we need this result in the proof of our main theorem. So let us recall the theorem. So proof of the main theorem. What is the main theorem? The main theorem is x. What are the given conditions? X is a locally compact vector space. These are the assumptions that we make. These are the basic assumptions that we make. What more? We are given some open set U in B such that K is let me such that K is contained in U, where U is open so you are given X, then you have a compact set K given, you have an open set given, then what we assert is that then the claim is, so these are the given conditions. You can say straight away say such that P A is contained in U. And obviously V closure is contained in closure is contained in. Okay. So you can, what it says is that there is sufficient room between K and U. Okay, there is sufficient room between K and this is the statement that we are. Okay. Let me go back to the same example that I said. If 0, 1 is a compact set in R, this is equal to K. 0, 1, if it is contained in some open set A, then A less than 0 and B greater than, then what you have is that if this is so, then there is, because of the structure of the space, namely it is a locally compact Hausdorff space, there is some open set there. For instance, you can take the open set to be what is it? A by 2 to what you call so this contains, so this is open, take B to be, and you have this, so this is U. Now you see that B is contained in V closure, which is equal to sorry, it's not B1, that's not. It's actually 1 plus what you have is B minus 1. So actually B plus 2 divided by B plus 1 by 2. So this is actually B plus 1. This is B share, and this is obviously, okay. And you have this result that this is obviously is. Now this is the implication. Now if this is true for any open set that contains, this is something that follows from the structure of the space. Now let us try to prove this theorem. Now you see that every point of K as a neighborhood an open neighborhood whose closure is common. Okay. Now what you do? You take K, right? Now you see that let then omega p belonging to k is an open cover for k. Now k being compact, what is the conclusion? Just say there exists a finite set. There exists a finite collection of points p1, p2, etc. pn such that k is contained in omega p1 this is the finite subcover. Yeah, that's the conclusion that you can make. Now obviously omega p is compact, therefore so here we use the locally compact property. Okay. Now and what do you have? This is what you have. Then k is contained in now let us use a more convenient notation. We use a convenient notation. Then G is open and we have K, G, okay. Now suppose Suppose u equal to x. Then it is not complicated at all. Then choose b to be equal to, so that we have the following, that is k contained in b, the closure is contained in obviously u, which is equal to x. That is obvious. So the problem is solved if you have u equal to x. Okay. Now we take the case where, so this is the part, we assume that this is assuming u equal to x. We have now suppose that is u is an open set contained in x with the property that k is contained in. Okay. Now the construction is a bit more complicated. What one does is the following. This is where we will have to use the tool that we have just now established. So the scenario is the following. Okay, this is what you. Okay, so you have k is contained in and u is not. This is open. Okay, now what we do is take up the scenario. So this is your x. This is your a. U is somewhere. U is not x. Now what one does is the following. Let C be equal to 2 combinations. That means this is your C. And C is closed. Then C is closed. Okay. For every P belonging to C, okay, you take some P over here, then there exists a WP which is such that K is contained in W and P does not belong to closure. Okay, so that means you have an open set here you have an open set here, say WP, such that WP closure does not contain. Okay, because it goes up to the boundary and you can actually separate to see that WP is properly contained. It doesn't, the boundary of that does not boundary. That's a conclusion. Okay. Now let P range over every element of C. That means you take the WP is corresponding to every P belonging. So we'll have to use this. You know that K is contained in every one of these WPs. Okay. Now look at this set. C intersection G closure intersection WP. Okay. So we take P belonging to C. So what you are taking is WP closure and C is there, the intersection of C with W closure. So what one gets is that, and you take G closure is what is the covering that we have already built for K, right? Okay, therefore G is K is contained in G. Now this collection is a compact space. Because you see that and the intersection this is empty. Now this is the only point that we have to solve. Okay. Now what one does is this. Therefore, since this is empty by the previous result, we have that is because C and this part are you know C and this part is non-intersecting. That is the reason. By the previous results, there exists a finite subcollection C that E1 be the elements of C such that G closure then what you have? So choose V to be equal to, or define V to be equal to G now this is a finite intersection of open sets, therefore V is open. Now V closure is equal to G closure intersection WP so what one gets is that K is contained in V, okay, and that is contained in V closure, and that is contained. Now the last part comes from this empty intersection. Okay, so this is the question. Okay, so this completes the proof. Okay, now we shall stop today with this and then introduce the concept of lower semi-continuity and upper semi-continuity, and then continuity and so on in a general scenario, and later go on to exploit this particular result in the construction of some continuous functions. Essentially, as I was telling, that this result tells you that there is a significant gap between k and u, so that you can keep the function to have the same a value 1 on this, and outside u identically 0, and in between patched up through a continuous function. Now this is a sort of utility that we are aiming at. Okay? Thank you very much.